We have already learned that interpolation is a useful tool for estimating function values when we do not have precise data. Suppose now we have three data points: the average national gas price of gasoline in the US on the 1st and 29th of December 2014 and the 26th of January 2015. The question is, how would we estimate the average cost of gasoline in the US on the 12th of January 2015? Again, this data is taken from the EIA.gov website. As before, it is a good idea to plot the data. Here we have plotted the three data points that we were given. Unfortunately, for this example, a straight line does not fit the data well. So, what are our options? Well, the first thing we could do is to find the best straight line that fits the data. This is known as least squares linear interpolation. Alternatively, we can fit a higher order polynomial. In this case, since there are three data points, we can fit a quadratic polynomial to the data. In general, if you had n data points, we can fit a polynomial of degree n minus 1 to the data. This is often known as Lagrange Interpolation. So, let's recall what we learned for linear interpolation. Given two data points, x1, y1, x2, y2, we gave the formula for this linear interpolating polynomial. And this formula works specifically because these terms simplify when x is equal to x1 or x2. For example, when x is equal to x1, this term simplifies to 1, and this term simplifies to 0. And when x is equal to x2, this term simplifies to 0, whereas this second term simplifies to 1, so that this interpolating polynomial gives exactly back L of x1 is y1 and L of x2 is y2. So the question is, what do we do when there are three data points: x1, y1, x2, y2, and x3, y3? Well, we can actually construct something very similar. It looks a little more complicated now. There are 3 points, 3 data points, so we have 3 terms here, and each of the terms look a little bigger. But really, they try and accomplish the same thing. So let's look at this first term. If we plug in x equals x1, then this term simplifies to 1. And if we plugged in x equals x2 or x equals x3, then this term simplifies to 0. So if we examine the rest of the other terms, you should be able to see the same pattern. So indeed, this polynomial L gives L of x1 is y1, L of x2 is y2, and L of x3 is y3. So L is the interpolating polynomial. The other thing we should observe is that each of these individual terms are really quadratic polynomials. So if you multiply it out, you get some coefficient times x squared plus some coefficient times x plus some coefficient. So by summing all 3 terms together, we get a quadratic interpolant. So if you have n data points, you can actually write a general formula. So although this looks intimidating, realize that these are really just the quotients of x minus xi divided by xj minus xi here. And it's missing the term x equals xi. So this interpolating polynomial can be written compactly using this product formula. So product says takes each of these terms for j equals 1 to n, but j not equal to I, and multiply them together. A quick word of warning: although Lagrange polynomials are easy to derive, these high-order Lagrange polynomials are very oscillatory. So back to our example. Let x be the number of days from the 1st of December 2014. So really we have the 3 data points. 0, which is the 1st of December, has a gasoline price of $2.74 per gallon. On the 29th of December, this is represented by x equals 28, and there's a gasoline price of approximately $2.23 per gallon. And then on the 26th of January, this is x equals 56, and that was $1.98 per gallon. So using the formula to generate the quadratic interpolating polynomial, we can form what this quadratic polynomial is. Now, if we want to evaluate this polynomial at a date, say January 12, 2015, since this is 42 days from the 1st of December, we get that L of 42 is $2.07. That is approximately on January the 12th, gasoline prices were approximately $2.07 per gallon.